In this lesson, we're going to look at representing enthalpy changes. Now, we could communicate enthalpy changes in one of these four different ways that we're going to look at in this video. One of them is to include an energy value as a term in a thermochemical equation. So what we're going to have is pretty much our typical balanced equation, right? Well, we will have our reactants to form our products, and the terms that we'll have in terms of our reactants and our products will be really the compounds that are involved with this reaction. But one of the terms will actually include some kind of an energy value. Another way in which we can show enthalpy change is by writing a chemical equation as normal, but then off to the side of the equation, we are going to state that the change in enthalpy will be whatever value. Third method is to state the enthalpy, the molar enthalpy of a specific reaction. Now, the key word here for this molar enthalpy is really what we're looking at is really what is the enthalpy change for 1 mole of whatever is our compound in question. And this will make a little more sense when we actually go through an actual sample problem and an example. And finally, drawing a chemical potential energy diagram, as you've seen in one of my previous videos on molar enthalpies. So, first method, thermochemical equations with energy terms. So, we're going to look at the electrolysis of water, which happens to be an endothermic reaction, meaning it's going to absorb energy from its surroundings. So here is the example. So typically, if we were to write this equation, we would write it based on just that. But now, a thermochemical, this is a chemical equation without this, but this is called a thermochemical because we have included the fact that this is the energy that it's going to absorb. It's going to absorb 285.8 kilojoules, right, of heat, of energy, for this reaction to actually occur. Combustion of magnesium is considered an exothermic reaction, and it's going to release energy. And so when we release energy, well, here without this is our typical chemical equation. But now we include this, and this now is considered a thermochemical equation in which the energy is shown here on the product side if it is exothermic, which means this is the amount of heat that is going to be released. The change in enthalpy will be 601.6 kilojoules that is going outwards into the surroundings. So here, right, in an endothermic reaction, right, we have our value pretty much on the side of the reactants. And in terms of an exothermic reaction, we have our value here on the side of the products. Because it's the products that are going to be, when the products actually form, this is where that release of that, that heat is going to actually occur. This sample problem. Write a thermochemical equation to represent the exothermic reaction that occurs when 2 moles of butane burn in excess oxygen gas. The molar enthalpy of combustion of butane is negative 2,871 kilojoules per mole. So what we want to do is we want to start off with our balanced chemical equation. Right? So now the key though is we're being told that we've got 2 moles of butane. So we want to make sure that when we balance this equation that this remains as is, right? To show us the 2 moles of butane. Now what we have here is we have this this molar enthalpy, right, our delta H of a combustion reaction being equal to minus 2,871 kilojoules per mole. Now, thing is though, we can use one of two things, one of two strategies, right? Remember this equation here, delta H is equal to N multiplied by delta H of whatever the reaction is, right? The reaction is combustion. So we're going to take this value multiplied by N to give us our delta H. However, another way you can do it is, well, here's this value based on, right, with this equation, right? But this is the combustion of butane. It's the molar enthalpy of butane, which means this is represented only by 1 mole of butane, not 2 moles. So to show 2 moles, what we're going to do is we're going to take this value here and we're going to multiply it by 2. Or in other words, we're going to substitute our N value here by 2 and this delta H of the reaction by negative 2,871 kilojoules per mole. And we're going to get a delta H, our delta H of the following to being minus 5,742 kilojoules. Now, that's not it, right? The question says, write a thermochemical equation. So a thermochemical equation includes, right, includes this balanced chemical equation. But because our value is a negative value, right, for our delta H, this means that our reaction is exothermic. Which means because it's an exothermic reaction, this value is going to be on the side of the products. So to write this thermochemical equation, it's going to look as follows. 2C4H10, and it's a gas reacting with 13 moles of oxygen gas. Remember, don't forget to include the states of matter, to produce 8 moles of carbon dioxide gas plus 10 moles of water liquid, and we're going to include plus 5,742 kilojoules. Notice how we are not referring to it as kilojoules per mole, because if we looked at this equation here, right, 2 moles, kilojoules per mole, moles divide out, and all we're left with are kilojoules. Now notice here we also put it down as a plus. When we are writing thermochemical equations, we show the positive negative value by depending on which side of the reaction we're actually going to write this on. If we write this delta H on this side of the reaction, it's exothermic, right? If we write it on this side, right, it would be considered endothermic. So in terms of this reaction here, the combustion of butane is an exothermic reaction because this amount of heat will be released. Sample problem. Write a thermochemical equation to represent the dissolving of 1 mole of silver nitrate in water. The molar enthalpy of solution is plus 22.6 kilojoules per mole. So because this value is positive, we know that it's endothermic. Which means when we are writing this value in terms of a thermochemical equation will be on the side of the products. So what do we have? Well, we've got AgNO3, and it's a solid. So silver as a solid in water, right, will form pretty much aqueous silver. And it will form aqueous nitrate. However, one more part is missing, Well, we're going to put here plus 22.6, but not kilojoules per mole, but kilojoules. So the molar enthalpy, so for 1 mole, right, so 1 mole of AgNO3 will pretty much absorb this amount of heat in order to form its respective ions when dissolved in water. Right? But in terms of heat, really, this is the amount of heat that will be, it won't go in that direction. It will actually be absorbed. Method number 2, thermochemical equations with the delta H values. So now pretty much we're writing very similar to what we've already done, right? But now looking at that electrolysis of water, as we said, is an endothermic reaction which is absorbing energy. However, this is our typical balanced chemical equation. So in a thermochemical equation with delta H values, we are going to state our delta H off to the side. And notice the value here. The value is positive because, as we've said in a previous video, a positive change in enthalpy, this delta H, is pretty much for endothermic reactions. Now, that same combustion reaction that we saw in the previous slide, or earlier on in this video, the combustion of magnesium, as we said, is exothermic. So again, here is a balanced, or our equation, right? And our change in enthalpy here is minus 601.6 kilojoules. So as we've said before, in an exothermic, right, we have a negative value for our change in H. The synthesis reaction of methanol by reacting carbon monoxide and hydrogen gas looks as follows. So carbon monoxide gas reacts with 2 moles of hydrogen gas to produce 1 mole of methanol. So our delta H here for this entire reaction is minus 128.6 kilojoules. So notice here that this is a negative value. Right? So therefore, this reaction is exothermic. And also keep in mind with these reactions, again, we're looking for this delta H value. Right? Now, another thing to keep in mind is the fact that our units for our delta H is in kilojoules, and they're not in kilojoules per mole. So they are actually in kilojoules. Now, because the enthalpy change applies to the reactants and the products given in the equation. So this whole equation will have an enthalpy change of the following. So we don't care whether it's 1 mole or 2 moles or 3 moles. Right? This value here will change, determining dependent on which one of these we are going to state what we call molar enthalpy. So this is an enthalpy change, not a molar enthalpy change. When we're dealing with molar enthalpy change, as we've seen before, the equation delta H is equal to the number of moles multiplied by delta H of whatever the reaction would be. So in this reaction here, well, this reaction, right, depending on however many moles we are looking at, right, will change our delta H. And we'll see a little more about this when we actually go through an actual sample problem. Now, here we have the following. So what we've done is we've reduced this 2, right, to find 1 mole of hydrogen that we're going to use, right? In this equation here, we're using 1 mole of carbon monoxide to 2 moles, right, of hydrogen to 1 mole. So if we wanted to reduce, if we wanted to simplify this 2 to a 1, we divide all moles, all the moles in this reaction by 2, and hence we're going to get the following. Right? Notice here, which is really a 1, and notice this being a half. So now note this change. Let me erase this here. Note the change in the enthalpy change. So the enthalpy change, if you compare this to this, we've divided it by 2. So what we could also look at is this could also represent the change, the molar enthalpy, right? The molar enthalpy of 1 mole of hydrogen, right? So in 1 mole of hydrogen, we are going to have a change in enthalpy of minus 64.3 kilojoules, right? But if we were looking at this equation here, this is dependent on 1 mole of carbon monoxide, 1 mole of methanol, and 2 moles of hydrogen, so it didn't really matter. Sample problem. Sulfur dioxide and oxygen react to form sulfur trioxide. The molar enthalpy for the combustion of sulfur dioxide, right, delta H and combustion, in this reaction is minus 98.9 kilojoules for every 1 mole, right, of SO2. What is the enthalpy change for this reaction? Now, a few things to make note of. We've got a negative change in enthalpy, which means we know that this reaction is exothermic, right? So what we're going to do is we're going to write a balanced equation. So what we have is, well, we know we have sulfur dioxide and it's gas, and it will react with oxygen gas to form sulfur trioxide gas. Oops. So to balance this, well, our numbers will be as follows. We put a 2 here and a 2 here. However, for this reaction, right, we have this based on 1 mole. So 1 mole of sulfur dioxide, right, has a change in enthalpy for this combustion reaction of minus 98.9 kilojoules, right, again, per mole, right, for every 1 mole. But we don't have 1 mole, we have 2 moles, right? So what do we have? Well, we have our delta H, because the question says, what is the enthalpy change? And this is the enthalpy change, is equal to N multiplied by our change in enthalpy of whatever the reaction is, which in this case is combustion. So how many moles do we have of sulfur dioxide? Well, we have 2 moles of sulfur dioxide, and let's start changing some colors. So we have 2 moles of sulfur dioxide multiplied by minus 98.9 kilojoules per mole of pretty much the molar enthalpy. And notice here, moles are going to divide out, and our change in enthalpy for this reaction is equal to minus 197.8 kilojoules. So to write this in terms of a reaction, so what we have here is, well, this is our change in enthalpy, and what we would do is we would put this off to the side of this equation here. Delta H is equal to minus 197.8 kilojoules. So we write our equation, right, because we're writing a thermochemical equation, but with our delta H value written off to the side. We are not going to include it as one of the terms in our equation, which if we were, actually, we would be putting it right here on the side of the products. Next sample problem. Write a thermochemical equation including a delta H value to represent the exothermic reaction between xenon gas and fluorine gas to produce solid xenon tetrafluoride, given that the reaction produces 251 kilojoules per mole of xenon reacted. So what we have is, well, we've got our xenon gas, which is going to react in the presence of fluorine, as we said, to produce xenon tetrafluoride. And this will be in solid form. So, now, what we have here is just our equation. So now we want to balance this. Right? So we want to balance this. So to balance this, we're going to put a 2 here. So we know that we are producing this much, or our molar enthalpy, right? Our molar enthalpy, here, our delta H, which is really equal to our N of the H, and we're looking at of a formation, right? Because we're actually forming something, so formation. So really, how many moles of xenon do we have? Well, we only have 1 mole of xenon, right? So in other words, this value, these two values are actually equal to one another. So our delta H really doesn't change, because look at this. The number here in front is really represented by 1 mole. So our value here is equal to minus 251 kilojoules. And why is it a minus 251? It doesn't show it here, but if we look closely into this question, look what it says here. Exothermic reaction. So in an exothermic reaction, as we've said before, our value here must show a negative for our change in enthalpy. The next method, as we've kind of touched upon just before the sample problems, is the molar enthalpies of reactions. Now, molar enthalpies of reactions, delta H of and X represents whatever the reaction happens to be, is the energy change associated with the reaction of 1 mole of the substance. So if we look at these examples here, right, we're looking at the solution, right? So what's involved here? Well, we're talking about 1 mole of this, I guess, this reactant here, sodium bromide, that will pretty much dissolve in water, right, forming the solution. We're looking at here a combustion reaction. So of course, what are we combusting? Right, our hydrocarbon. We're vaporizing. What are we vaporizing? The methanol. What are we freezing in this example? The water. What are we neutralizing here? And now with neutralization reactions, we can either neutralize the acid, and we're looking, or the base. And of course, with these, whenever we're dealing with molar enthalpies, whichever compound is the compound in question, we always want it to be represented by 1 mole. So notice all of these, right? All of these are represented by 1 mole. Right? Now, see here with this 1 mole, right? Notice this is the reason why we have 2 variations of this equation. Because in this equation, our acid is 1 mole. And we have 2 moles of the base. But if we're trying to look at the base, right, and find the molar enthalpy of sodium hydroxide, we need to simplify this 2 to 1, as we do here. Hence, all the others get divided by 2 to get this second variation of a change in enthalpy and the molar enthalpy of this neutralization reaction. And this formation we're going to see a little more later on. And of course, one of the difference here with the molar enthalpy of a formation, right? We're forming something, right? So what are we forming? We're forming this methanol. So that's the one that we'll be looking at in terms of 1 mole of that product. Now, a molar enthalpy that is determined when the initial and final conditions of the chemical system are at SATP. So we've looked at the standard ambient temperature and pressure, right? So the molar enthalpy is no longer the molar enthalpy, but it's referred to as the standard molar enthalpy of a reaction. And the standard molar enthalpy of reaction, one of the differences, well, here, molar enthalpy, we're looking at delta H of some kind of reaction. But the standard molar enthalpy of a reaction, change of a reaction, will have this little knot here, almost like a degree symbol. and we will include that when we're referring to 1 mole of a substance, but that is in standard conditions or standard ambient temperature and pressure. And this energy change is associated with the reaction of 1 mole of a substance at 100 kilopascals and a specified temperature, which is referred to at 25 degrees Celsius. So the symbol delta H naught of whatever the reaction is here distinguishes standard molar enthalpies from actual molar enthalpies that we've looked at before, which are measured at other conditions of temperature and pressure. So if we're referring to it in this, we know that the pressure and the temperature are at those values. Now, chemists have determined the standard molar enthalpy of reaction for methanol in this reaction. So what we have is the delta H, the standard molar enthalpy of this reaction, to be minus 128.6 kilojoules per mole of methanol. Right? So here is our reaction. Notice we are referring to 1 mole of methanol, and that's hence the reason why we have the per mole. Right? So our delta H, our molar or standard molar enthalpy, is that. Now, right? This is our value. Right? But now find the delta H, right? Find the molar enthalpy change for 1 mole of hydrogen. Right? But look at how many moles of hydrogen. We have 2 moles of hydrogen. So to find 1 mole of hydrogen, we need to divide this by 2, which means whatever I do to that, I must do to all these, right? The 1 that's here, this 1 divided by 2. And I'm going to get 1 over 2 carbon monoxide gas plus 1 mole of hydrogen gas to produce a half mole of methanol. So in other words, now this delta, this molar enthalpy, or the standard molar enthalpy of this reaction is actually equal to, well, since we've divided this reaction by 2, we need to divide that value here by 2. So when we divide this value by 2, we are going to get a value of minus 64.3 kilojoules per mole of hydrogen gas. Let's look at this sample problem here. Write an equation whose energy change is the molar enthalpy of combustion of propanol. So really what we're doing is we're starting off with an actual chemical equation for the combustion of propanol. So we have C3H7OH. It's going to burn in the presence of oxygen. Gas, of course, and we've got gas. To produce CO2 gas, right, carbon dioxide, as usual, plus water. Now, we want to balance this equation. Now, however, we are being asked to write an equation to show pretty much the molar enthalpy of the combustion. We're not going to actually show any numbers because there are no values here given, right? Unless we're given those values. But we want it to show really 1 mole of propanol. So in order to do that, when we balance this equation, these are the values that we're going to get. We're going to get 9 halves of oxygen, 3 moles of carbon dioxide, 4 moles of water. Typically, when we would balance this, right, we wouldn't want halves, right? So we would multiply all these terms by 2 to get 2 moles of this, 9 moles of this, 6 moles of this, and 8 moles of this. However, we are being asked to write it in a way where we will show molar enthalpy. Molar enthalpy is always related to 1 mole of the compound in question, because this 1 mole that's required is required for combustion. What is combusting in this reaction? It is this part right here. So this reactant, this part of the reactant, must show 1 mole of it. So the actual equation for it will be here as shown up top. Ignore these. For this sample problem, really, again, same thing. Write an equation whose enthalpy change is the molar enthalpy of the reaction of calcium reacting with hydrochloric acid to produce hydrogen gas and calcium chloride solution. Right? So we're going to have calcium solid plus hydrochloric acid, which is aqueous, to produce hydrogen gas and calcium chloride, which also is aqueous. Now, again, our delta H has to equal the delta H of this reaction, right? So in other words, the molar enthalpy has to equal to the change in enthalpy. So if we're getting the molar enthalpy, we're referring to, again, 1 mole in this reaction. So we want just 1 mole. So we want really 1 mole of calcium. Right? So we want 1 mole of calcium. So to balance this, our numbers will look as follows. We put a 2 here again, and we leave it as such, right? Because we are showing 1 mole of calcium. So if we were given any of the values, of course, our delta H would equal to our, so our change in enthalpy will equal to our molar enthalpy. Final method, potential energy diagrams. Chemical potential energy is the stored energy is related to the relative positions of the particles and the strengths of the bonds between them. Right? So there's a potential energy that's actually stored within the bonds of our reactants, right? We're going to pretty much get released, right? Depending on really positioning of the particles in the change, right? With whatever's occurring. Because remember, we're looking at the reactants versus the products. So, where is there more energy? Is there more energy stored here than there is here? Or vice versa, of course. That's really what we're trying to identify. And that will determine whether something is considered exothermic or endothermic. So as the bonds break here in the reactants and reform, right, the positioning of these atoms, right, they also change, right? And this will also change occurs in potential energy, right? So there's a new potential energy in the reactants. So is the potential energy in the reactants greater than the potential energy in the products? Or is there more potential energy in the products than there are in the reactants? So the potential energy change in the system is equivalent to the heat transferred to or from the surroundings, right? And we've shown this with the following diagrams. The energy transferred during a change is represented as a change in the chemical potential energy of the particles as bonds are broken or as they are formed, right? So we've looked at these type of energy potentials, right, for exothermic and endothermic. And let's just recap a few things. We know that in an exothermic reaction, temperatures will increase. More specifically, of course, the temperature will increase from an initial to some kind of final temperature, right? What else? Well, our delta H, or our change in enthalpy, is a negative value, right, for an exothermic reaction. And for an endothermic reaction, temperature we know is going to decrease, right? So the initial temperature will be higher, the temperature of the surroundings will decrease and result in a change in enthalpy that will give us a positive value. Now, for such a reaction, right, we are going to have the following. Well, we're going to, in an exothermic reaction, the potential energy is higher in the reactants than they are in the products. And the products are lower. And this is just a recap of what we've already talked about in the past. So what we have here is, well, here we've got now what we call pretty much our change in enthalpy. So the reaction is going this direction. So all of a sudden, the reactants have a higher potential energy. So of that potential energy, when the new bonds form in the products, that energy, that heat, gets released. So that change in enthalpy, right, this will give us a negative value for our change in enthalpy. But over here on the reactants, or sorry, for the endothermic, our reactants actually have a low potential energy, while our products have a higher potential energy. So here we have our reactants, here we have our products. So when the products form, they will store so much more energy. Why? Because when these bonds get broken, right, when these bonds get broken in the reactants, that energy gets stored into the particles that, or the bonds that form the products, right? Hence the reason for a positive value for a change in enthalpy, right? So we're increasing in the amount of potential energy in our products. Let's look at the following example here. So here we have magnesium reacting with half a mole of oxygen to form 1 mole of magnesium oxide. And all of a sudden we have our energy value over on this side of our equation. So what does that mean? Well, it means that this reaction is exothermic. And as we said, in an exothermic reaction, the delta H is a negative value, 601.6 kilojoules. Right? So then now here at the bottom now, we've got water, right? The electrolysis of water requires energy to be absorbed here, right? This is an endothermic reaction, right? So this is endothermic because energy is being absorbed, right? This amount of energy is being absorbed to break down the water into 1 mole of hydrogen gas and half a mole of oxygen, right? So how are we going to draw these two reactions on their respective tables? So here, as we said, in an exothermic reaction, we know that the reactants have a high potential energy, while the products will have a lower potential energy, which will result in a change in enthalpy, right? Change in or molar enthalpy, right? Standard molar enthalpy in this formation reaction, right, of minus 601.6 kilojoules. Now, if we look at, and this is the amount of heat that's going to be released. Now, if we look at the this other one, the pretty much the decomposition or the electrolysis of water, right? This decomposition of water. Well, the water itself has a low potential energy, so it's going to absorb the energy and all of a sudden store that energy in the products, right? So the products now will have the greater potential energy. So now the delta H is rising, right? So that delta H, the standard molar enthalpy, right? Again, and notice we're referring to 1 mole, and here 1 mole, or even 1 mole of because it's formation, 1 mole of each substance, and it's a decomposition reaction. Right? Decomposition reaction is equal to 285.8 kilojoules. Sorry for my penmanship here, trying to write with this tablet. So notice here the value for an endothermic is a positive delta H. For an exothermic, it is a negative delta H. Sample problem. Write the symbol and calculate the molar enthalpy of combustion for the substance that reacts with oxygen. So what we have here is the change in enthalpy based on this entire reaction. And because it's on this side, we know that this is exothermic. Right? So it's exothermic, but now we want it to be the molar enthalpy. So we want 1 mole, but if we look at it, we have 4 moles of ammonia reacting with 7 moles of oxygen to form 4 moles of this gas, nitrogen dioxide, and 6 moles of water vapor. Right? So none of them are represented of 1 mole. So now the thing is, this question says combustion. So what is combusting in this equation? This is what's combusting. However, we have 4 moles, right? And this value here is based on 4 moles. So we want the molar enthalpy. This is not the molar enthalpy. This is the delta H. This is the change in enthalpy. We want the change in enthalpy based on a combustion reaction. And based on a combustion reaction, we are always referring to this in terms of 1 mole. So to get 1 mole, we're going to divide this by 4, which means if we do that to this, we're going to divide this value here also by 4. And what are we going to get? Well, we're going to get a change, and let me erase some of this. We are going to get a change in molar enthalpy based on a combustion reaction. And we're going to get a value of minus 283.6 kilojoules per mole, right? Because we're talking about 1 mole. So for every mole of ammonia that we are using, we are giving off this amount of heat. Now, because we are giving off, we're combusting 4 moles of ammonia, notice it is releasing so much more heat. Let's look at the next sample problem here. We've got 2 moles of nitrogen combusting in the presence of oxygen gas, and it is absorbing 163.2 kilojoules to form 2 moles of dinitrogen oxide gas. So because this value is on this side, we know that this reaction is considered endothermic. But now, this value, this delta H, right, that we have is based on 2 moles of N2 that is combusting. We want it based on 1 mole. Right? We want it based on 1 mole. So 2 moles will form 163.2 kilojoules. So 1 mole, we're going to divide this by 2 to get the following value. We're going to get a delta H of combustion, right? Because we're asked for the molar enthalpy, that will be 81.6 kilojoules per mole of N2. And again, if this one here is of NH3, because that's the one that we're trying to find 1 mole of. So notice it's a positive value because it is considered endothermic.